I'm Miss Darden, and this is part 2 of our rational functions video series. And today we're going to talk about those, continue talking about those discontinuities and go into more detail about the removable versus non-removable. So we talk about the excluded values causing a break in the graph, but what does that break look like? Well, there's either two things it could look like. It can either look like a vertical asymptote, or a hole in the graph. Okay, so a vertical asymptote is the non-removable discontinuity type. It's non-removable. That's that thing where when you reduce your fraction, it doesn't go away. So if you're looking for like a real world way to explain that, it's the part of the bottom that does not cancel. Part of bottom of fraction that does not cancel. Does not cancel, non-removable. Okay, and then the other type of excluded value or discontinuity that we discussed in video 1 was the removable discontinuity. A removable discontinuity is one of those things on the bottom of your fraction that does reduce or cancel away when you're, reducing or simplifying that rational expression. The result of that, though, it still has an effect on the graph, and that effect is a hole in the graph. So holes are removable discontinuities. It's the part of the bottom that does cancel. Once you find that value, you have an extra step with the hole, because the hole is like an ordered pair, but when you get to that ordered pair, there's nothing there. There's just a hole in your graph. But I need to find that ordered pair location. So with your excluded values, we just found x values. A vertical asymptote will look like x equals, but a hole will look like an ordered pair. So if we have the x value, what we have to do to find the y value is plug the x value back in. So right here, this is important. Plug your x value into the reduced fraction. That's important. Labeling these properly is important. Okay, so let's try some examples. And if we're continuing on from our example list from the last video, I gave you 2 examples in the first video, and now I'm going to give you 3 more. So we're going to start with example 3, just to continue that list. I've already factored this first one. 2 times x plus 1 over x times x plus 3 times x plus 1. We're going to cancel. X plus 1 and x plus 1 reduce. Okay, so let's list what we know. We know that we have discontinuities. Here at 0. Here at -3, and here at -1. I want you to now tell me what type of discontinuities they are. I want you to get more specific. So let's look at this one. Did 0 go away? Were we able to cancel it? No. So that is non-removable. I can't remove it because this reduced to 2 over x times x plus 3. I could not remove the x. It's still there. So it's a vertical asymptote. X equals 0. X plus 3. It did not cancel. It's still there. We did not remove it. So it's also a vertical asymptote. And x plus 1 resulted in a -1 excluded value. It was able to be removed or reduced. See, it's not there in the reduced function. The result means this is where our hole is at. So we have a hole at -1. But a hole is an ordered pair location. So I've got to figure out the y value for that. And in order to do that, you have to plug that in here. So I'm going to take 2 over, and we're going to plug in a -1 everywhere we see an x value. -1. Again, you take your x value, you plug it into your reduced function, and that's how you find your y value of your hole, the y location of your hole. Let's try example 4. I did not factor this one first. You're going to have to factor it first. You just can't cancel these x's. Killing kittens. Don't do that. First sign comes first. Signs have to be the same. First number comes first. There we go. So our discontinuities at +1. What type of discontinuity is it? Well, that thing reduces, it goes away. So do I have any vertical asymptotes left on the bottom? No. So vertical asymptotes are none. Do I have any holes? Yeah, I got a hole right here at this removable discontinuity. It's a +1. Because if I set this equal to 0, I'd get a +1 for a discontinuity. And then don't forget, you have to plug this in to your reduced function. I did that. X minus 3 is the reduced function. Plug in a +1 there, and you get out a -2. So my hole is at 1, -2. It's just that easy. Just that easy. Example 5. 2x over 3x squared plus 1. Nothing factors out. This is it. So for our discontinuities, we got to take our bottom and set it equal to 0. This one looks weird, right? I can't just really eyeball that. There's an x squared there. So if I take 3x squared plus 1 and set it equal to 0 and solve for x. The square root of a negative is imaginary, isn't it? And eventually you will get really good at this part. I don't care about this so much. I care, can you get right here and recognize that that is imaginary? If it's imaginary, excuse me, we don't have a vertical asymptote or a hole. If there is no real solution, then we have no discontinuity. or actually no vertical asymptote or hole. No vertical asymptote and no hole. So there's your breakdown of types of discontinuities. These are super important, and we will always do this step first. You will always factor, reduce, list your discontinuities or excluded values, and then you're going to categorize those. They either have to be vertical asymptotes, meaning they do not cancel, or holes, meaning they do cancel or remove. You should be able to now start on your rational functions packet and do 1 through 10 where you list the vertical asymptotes and holes.